what is it about? This is about the simulation of the different frequencies in different areas of the brain. And the idea is try to connect two different networks. The network that was simulated in the last video. And the idea is try to connect by different mechanisms these two networks, and try to reproduce the different frequencies and oscillation that are found in the brain, in the human brain and the rat brain. Okay. The brain areas that has presence of these oscillations are three: the prefrontal cortex, the visual cortex, and the hippocampus. Then in these three different areas we can find this behavior of the oscillations in the brain. But in this case we're going to simulate the prefrontal cortex simulations. How we are going to do it? Okay, we are going to we will have two different networks. The first one with a mean frequency of 20 Hz, and the second one with a mean frequency of 32 Hz. Then the idea is we're going to have inhibitory and excitatory cells here with a kind of a set of probabilities, and we're going to have here a network with another kind of inhibitory and excitatory cells with different probabilities. And the idea is try to connect it with different mechanisms that we're going to talk later.
In this model, networks are divided in slow and fast network according to frequency. Generally, the networks will or target or source network without reciprocating connection. We will see how the activity of the target network is disturbed. For the cells, the model with a conductance-based model with a compartment for each one. And for this, they use sodium channel, potassium channel, and leakage channel. In this table, we can see the different forms of relation between slow and fast network. The majuscule letter represents a fast network and minuscule letter the slow. In the columns, we have an interconnection constant. For example, in this column, we have that E majuscule is interconnected with E minuscule.
About the results, we're going to show you first how to generate it. Then the idea is really similar as in the first paper, in the first video. Then we have here to generate the DLL file. This was the folder of the first paper, but and this is the folder of the second paper. We have to go here, and we go to modes again, and we just generate the AL file. All things are okay. Then we go to exit and we open. Okay. After you can't forget that you have to copy this DLL file in the main folder, or the simulation don't go around. Then you open this window, and this appear. We change our working directory. We go to this one, and finally this one. We move to, and here the different modes files are charged. Then we just load the hook, this one, and we load. Then here a lot of windows appear. We have here different windows that give us information about the results. They give us graphical results for the different network. And here we have again, as the first model, the the control window, and here the simulation window. Then we just go to single run, and this begin to act. Okay, when this is okay, we go again to MATLAB, and we can see here in the folder the generated file. I go here, 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 and here, and with this file, with these different numbers, we can obtain the mean graphic.
Later, with the result from networks in MATLAB, run the MATLAB file, run sample files, and we obtain this feature. And the analysis of the network dynamics is made separate for the four population of the neighbor, the E and the I population of the slow network, and the E and the I population of the fast network, by means of Ramírez histogram, Fourier analysis, and Boolean analysis. To describe the network activity in each of the populations, we construct Ramírez histograms by coding space in time bins of 6 milliseconds. The fast Fourier transform of the activity in each cell population was computed on the basis of the Ramírez histograms of 40 seconds of activity, approximately. For each cell population, we identified the components in the last Fourier transform that were local maxima, and maximum of these components is then the peak frequencies of the particular cell population. The analysis to analyze how the power of the histogram varied over time, we perform a Boolean analysis using the Torres algorithm implemented in MATLAB with the convert Ramírez histogram as input.
What happened? What generate the model? The model generate this graphic here. Then this graphic show us three kinds of networks or models. The first one gives us just the slow network. It shows us the mean frequency 20 Hz, 20 Hz, and 20 Hz. Here is the fast network, 32 Hz, 32 Hz, 32 Hz, and here we have 32 Hz in time. And finally here, this is the most important result. We have the result of combine the two different network, the slow network with the fast network. Then what we obtain? We obtain a high frequency with the respect of this one and this one. Then we obtain, besides we obtain another important frequency. And then we have two predominant frequencies, and besides we have a high frequency in our model. As we can see here, that the pulses in the graphic is faster than here and then here. Okay. About the mechanism of connections, we have here in the first that, as we told you in the first video, the inhibitory connect with the excitatory, and the second one again, the inhibitory with excitatory, and this is the important. This tells us that here the inhibitory interact with the excitatory, as in this one and in this one, but in this case we connected the two different networks from excitatory to excitatory. That is our mechanism of connections. But you know that with different mechanism of connection, we obtain different results. Then for this result, the mechanism used was this one. Okay.